I want you to try and imagine a beam of intense focused energy.
Essentially a cosmic laser.
Right, a cosmic laser shooting across the absolute pitch black void of the universe.
Yeah.
Just entirely empty space.
And it's moving at the speed of light.
Exactly. It's moving at the speed of light, and it just keeps going. It travels for 1 billion years.
Then 2.
Then 4. It is soaring through the deep universe for 8 billion years.
Which is an unimaginably long journey.
It really is. And finally, after all that time after crossing the cosmos, it hits a network of highly sensitive radio telescopes right here on Earth.
Just arriving now.
Just now.
Yeah.
That ancient signal just arrived, and it is entirely reshaping our understanding of astrophysical emission mechanisms. So welcome to the deep dive. We have a profoundly fascinating paper to dissect today.
We really do. It is a staggering concept when you actually map out the spatial and temporal scales involved here.
Yeah, it defies logic.
It does. A journey of 8 billion light years completely defies our intuitive grasp of celestial mechanics. But the underlying physics of how that signal was generated and, how it survived that transit is what we are going to be exploring today.
Let's look at the source material driving this deep dive. We are analyzing a recent discovery, and this was published in the monthly notices of the Royal Astronomical Society. Letters.
A very prestigious journal.
Highly prestigious. And the researchers detail the detection of what is officially one of the most intense, energetic phenomena ever observed in the deep universe.
It's a finding that pushes the theoretical upper limits of what we call isotropic luminosity.
Meaning it's just incredibly bright.
Exactly. It forces a complete reevaluation of the models we use for cosmic energy emission. It is a phenomenal piece of literature. It details an observation that required an unprecedented alignment of deep space variables.
And some highly advanced terrestrial interferometry to actually capture it.
Yes. Our own technology had to perfectly align with the cosmos.
Which sets up our mission for today's deep dive perfectly. We are going to examine the specific quantum mechanics of what a cosmic laser actually is.
Because it's not a laser pointer in space.
Right, definitely not. We'll explore the complex interferometry and gravitational physics that allowed us to detect it from such a vast distance.
And dissect what this single data point reveals about the evolution of the universe during a really critical era of its history.
Okay, let's unpack this.
The observation itself is a triumph of modern radio astronomy, truly. The signal was captured by the Meerkat Observatory down in South Africa.
And we aren't talking about a single optical lens pointed at the sky, right?
No, not at all. Meerkat is an array. It's 64 individual radio dishes.
Right. And what makes Meerkat so formidable is how it utilizes interferometry.
Which is a brilliant workaround for engineering limits.
Yeah, because rather than building one structurally impossible kilometer-wide dish, which would just collapse under its own weight, the observatory links those 64 separate dishes together.
They meticulously correlate the phase of the radio waves arriving at each distinct antenna.
And by doing that, they synthesize an aperture equivalent to the distance between the furthest dishes in the array.
Exactly. It gives astronomers the resolving power and the sheer sensitivity required to detect an emission from 8 billion light years away.
And the source of this particular emission is a colliding galaxy system. It's a very catchy name, at Tellus J142935.3.
Dash 002836.
That's the one. Rolls right off the tongue.
It really does. But that specific coordinate designation places the collision right in the middle of a highly active epoch of the universe.
Right. But to understand what the Meerkat array actually detected coming from that system, we need to drill down into the emission mechanism itself.
Because the research team identified this not just as a standard radio emission.
Right, they identified it as a hydroxyl megamaser.
A hydroxyl megamaser.
Right. So when people hear the term laser, the mind immediately jumps to visible light,
Yeah, optical lasers driven by synthetic cavities in a lab.
Exactly. But out in the interstellar medium, we're dealing with masers. That stands for a microwave amplification by stimulated emission of radiation.
So instead of visible light, this system is beaming highly focused, intense microwaves.
What's fascinating here is the sheer scale of the stimulated emission.
A hydroxyl megamaser requires a highly specific environment to even form. You need incredibly dense molecular clouds, rich in hydroxyl.
Which is just one oxygen atom bonded to one hydrogen atom. Right?
Exactly, OH. And you need a massive pumping mechanism to drive what we call a population inversion.
And that pumping mechanism in this scenario is the galactic merger itself.
Yes.
We're looking at two distinct galaxies undergoing a violently chaotic collision.
Just smashing into each other.
Right, and as their respective interstellar mediums slam into each other, the kinetic energy generates these monumental shock waves.
Which compress the dense molecular clouds.
Exactly, and that compression bathes the hydroxyl molecules in intense infrared radiation.
That infrared radiation is the catalyst. It pumps trillions upon trillions of hydroxyl molecules into a higher excited quantum state simultaneously.
So they're all holding this extra energy.
Yes, that is your population inversion. The molecules are essentially primed. Then, when a background photon of the correct microwave frequency,
Specifically around 1665 or 1667 megahertz, according to the paper.
exactly, when a photon at that specific frequency passes through the cloud, it triggers a stimulated emission.
So a single photon drops an excited molecule back to its ground state.
Right, causing it to release a duplicate photon perfectly in phase, moving in the exact same direction.
So those two photons trigger four,
or trigger 8.
and you get an exponential cascading wave of coherent microwave radiation.
It is a naturally occurring optical amplifier on a galactic scale.
It's mind-blowing. The paper includes this great quote from astronomer Thotto Manamela of the University of Pretoria. He noted, quote, "We are seeing the equivalent of a laser beam coming from the other side of the universe."
Manamela's assessment is spot on. It really highlights the sheer coherence and intensity of the signal.
Yeah.
But the Meerkat data revealed something that elevates this observation past a standard galactic collision.
Right, the amplitude.
Yes, the amplitude of the signal captured at those specific hydroxyl frequencies suggests an isotropic luminosity that challenges the established parameters of what a megamaser even is.
Here's where it gets really interesting. Because the emission from the system is so luminous, the researchers argue it shatters the megamaser classification entirely.
They are categorizing this signal as a potential gigamaser.
A gigamaser.
Yeah.
We are talking about an emission profile that is billions of times brighter than a conventional stellar maser within our own galaxy.
Billions of times brighter. And a leap from mega to giga in astrophysics isn't merely a change in nomenclature.
It's not just a cool name.
No, it implies a fundamentally different physical regime. To generate a gigamaser, the volume of gas undergoing population inversion must be absolutely staggering.
It suggests that the colliding galaxies possess a gas fraction significantly higher than what we observe in the local universe today.
Which tracks perfectly with the 8 billion light-year distance.
Right, because if we look back 8 billion years, we are peering into an era astrophysicists often call cosmic noon.
Cosmic noon, a period roughly at a redshift of 1.5 to 2.
And that was when the universe was churning out stars at its absolute peak rate.
Galaxies during cosmic noon were chaotic, they were intensely gas-rich, and they were merging constantly.
The interstellar medium of a galaxy back then was thick with the raw materials necessary for star formation.
And consequently, hydroxyl maser production. The kinematic forces of a major merger during this epoch would funnel vast reservoirs of this molecular gas directly into the central regions of the collision.
Just feeding the reaction.
Exactly. It creates an unusually broad and deep amplification pathway for the background microwave photons to travel through, resulting in that gigamaser-level burst of coherent radiation.
But even acknowledging the immense power of a gigamaser fueled by a cosmic noon merger, we still have to confront the inverse square law.
Physics always wins out.
Always. Radiation propagates outward and disperses. Its intensity is inversely proportional to the square of the distance from the source.
So over 8 billion light years.
A gigamaser, no matter how luminous the source, it should have attenuated to basically background noise by the time the wavefront reached the Meerkat antennas.
The signal attenuation over that kind of baseline is absolute. Without an external modifying factor, the flux density of the microwaves arriving at Earth would fall well below the detection threshold of even our most sensitive interferometers.
So how did we see it?
The fact that Meerkat registered the 1665 megahertz spike means the wavefront was subjected to severe gravitational lensing.
Gravitational lensing, which is arguably one of the most elegant confirmations of general relativity.
We are dealing with an optical illusion dictated by the mass of the universe itself.
Right, so we have the gigamaser source 8 billion light years away.
And we have Meerkat here on Earth.
But positioned almost exactly along our line of sight is a massive foreground galaxy acting as the lens.
As Einstein outlined, mass dictates the curvature of space-time.
Right.
The gravitational well of that intervening foreground galaxy is so profound that it literally warps the fabric of the space around it.
So when the gigamaser's microwaves approach this gravity well, Their trajectory was completely altered.
Yes. The radiation followed the curvature of space-time, bending around the massive foreground object.
Instead of using the classic heavy ball on a trampoline analogy, which we hear all the time,
It's a bit overused.
it is. It is much more accurate to picture the base of a wine glass.
Well, that's a great way to visualize it.
If you hold the stem of a wine glass and you look through the thick, curved glass at the base toward a candle flame, the glass distorts the light.
Exactly.
Depending on the exact alignment, the glass might smear the flame into an arc or maybe duplicate it into multiple mirrored images.
Or, if the alignment is mathematically perfect, stretch the light into a brilliant continuous halo known as an Einstein ring. The wine glass analogy accurately represents the formation of caustics,
Costas.
regions of maximum magnification. In the case of Attilas J14293.5.3,
-002836.
right, the background gigamaser, the foreground lensing galaxy, and the Earth were aligned with such incredible precision that the diverging microwaves from the maser were bent inward and focused directly toward our solar system,
So the intervening galaxy acted as an objective lens.
gathering radiation that would have otherwise bypassed Earth entirely and concentrating it directly onto our detectors.
The magnification factor provided by that gravitational lens is the only reason the signal breached Meerkat's detection limits.
It's serendipity on a cosmic scale?
And it is a two-way street for astronomers. The lensing doesn't just amplify the background gigamaser. The specific way the light is warped allows physicists to map the mass distribution of the foreground galaxy itself.
If we connect this to the bigger picture, analyzing the exact geometry of the lensed microwaves lets researchers calculate the dark matter halo of the intervening galaxy.
Because dark matter contributes to the gravitational warping,
Oh!
just as much as luminous baryonic matter.
The utility of that cannot be overstated. We are utilizing a rare, highly luminous background event as a backlight to perform a volumetric scan of a completely different foreground galaxy's dark matter structure.
It is a remarkable confluence of physics that maximizes the scientific yield of just a single observation.
It really is.
So what does this all mean? For you listening, why does this matter? We have a hydroxyl gigamaser, triggered by a massive galaxy merger during cosmic noon,
Amplified by the space-time curvature of a foreground dark matter halo.
and detected by 64 phase-length radio dishes in South Africa. The mechanics are astounding, but what is the broader application of this discovery for the field of astrophysics moving forward?
The immediate takeaway is empirical validation. Detecting this megamaser and potentially classifying it as a gigamaser proves that terrestrial interferometry has reached a sensitivity threshold capable of isolating these specific molecular transitions across cosmological distances.
We proved the gear works.
Exactly. Meerkat is essentially a precursor to the Square Kilometre Array, or the SKA.
Right.
By proving we can isolate these lensed maser signals now, we are paving the way for the SKA to eventually catalog hundreds, if not thousands, of similar high redshift masers.
And building a deep space catalog of masers is a critical tool for resolving some of the biggest tensions in modern cosmology, isn't it?
Yes, masers are incredibly precise kinematic markers. If we can observe masers orbiting the supermassive black holes at the centers of these merging galaxies, the Doppler shifts in their microwave emissions give us exact measurements of the disk's rotational velocity.
And those velocity measurements, combined with the geometric distance to the maser, provide a direct, independent method for calculating the Hubble constant.
Which is the current expansion rate of the universe. Right now, there is a discrepancy between the Hubble constant calculated from the cosmic microwave background and the constant calculated using local Cepheid variable stars.
The crisis in cosmology.
Exactly. Finding more of these distant masers gives cosmologists an independent ruler to measure the expansion of the universe, potentially resolving that crisis.
Beyond the cosmological constants, these signals are pristine time capsules.
Very true.
Because the microwaves took 8 billion years to reach us, we are literally capturing the kinematic and chemical signature of a galactic merger right in the middle of cosmic noon.
We are directly measuring the density of molecular gas, the shockwave propagation, and the star formation rates of a universe that was entirely different from our current local group.
It provides a high-resolution data point for models of galactic evolution. It shows us how massive, gas-rich galaxies collided and exhausted their stellar fuel reservoirs.
I think it's vital to step back from the interferometry and the quantum mechanics for a moment. What stands out to you when you think about our ability to witness the violent birth of a cosmic laser from 8 billion years ago?
It's humbling.
Consider the sheer accumulation of technological advancement required to simply listen to the microwave static of the deep universe and pull out a coherent signal from a molecular cloud halfway across the observable cosmos.
It requires a profound shift in perspective. To recap the journey of this deep dive, we started with the violent collision of two gas-rich galaxies during the peak of the universe's star-forming epoch.
That kinetic impact drove a massive population inversion in hydroxyl clouds,
Triggering a gigamaser, a cascading release of coherent microwave radiation,
we traced those microwaves as they traversed the expanding universe.
only to be caught in the gravity well of a foreground galaxy, which warped space-time to magnify the signal just enough for the Meerkat Array's 64 dishes to synthesize the data.
The chain of causality is intricate. And as we conclude our analysis of this literature from the monthly notices of the Royal Astronomical Society, letters, this raises an important question.
What's that?
One that bridges the gap between observational astrophysics and the philosophy of time. The radiation required 8 billion years to transit the space between that system and our receivers.
Right.
The kinetic event that triggered the population inversion, the violent collision of those two galaxies, concluded billions of years before the Earth even accreted its first tectonic plates.
Wow. The delay in the light speed transit means we are analyzing an event that has been over for eons.
The gigamaser is essentially a ghost. The interstellar gas clouds have long since collapsed into new stellar generations or been expelled by active galactic nuclei.
The supermassive black holes of those two merging galaxies have almost certainly coalesced by now.
Exactly. The structure we just mapped using Meerkat has spent the last 8 billion years evolving into a dormant, elliptical galaxy that looks absolutely nothing like the luminous, chaotic system we are measuring today. What does it mean for our fundamental understanding of the universe when the energetic phenomena we dedicate our lives to deciphering are, in reality, ancient fossils of light?
Ancient fossils of light. The fact that we can decode the molecular chemistry of a galaxy that no longer exists in the state we are observing it is a testament to the rigor of the scientific method.
It really is.
It is a profound reminder of the temporal vastness of the cosmos and the sheer ingenuity required to read its history. Thank you for joining us on this deep dive. Keep questioning the universe, and we will catch you on the next deep dive.